All right. So we're 3D learning. We're in a finite MDP. We have this trajectory, and we use, this is our data. And based on the data, we want to come up with estimates of the value functions. The value function is what? It assigns a value to every state, and the value is just the expected return. If you are starting your process from that state, you follow the policy, and then you just get an infinite sequence of rewards, and you're discounting them. And this is defined for every state in our state space. 3D learning. There are many ways of writing it. So the last time I wrote it by writing it the following way: Vt plus 1 at S. You have a big bracket, and you have the convex combination of the previous estimate, and then you are mixing in a target where you're using a guess for what the future values are going to be. And you use this update when the state is the state that is currently being visited, and otherwise you're not changing the values. So it's like just you have this big vector that represents the value function, and you're updating one entry, the entry that the process is currently visiting in time step t, and all the other entries are untouched. So the last time I was arguing that this blending on an old gas with a new gas with a target is similar to what you do when you are trying to estimate the mean of some distribution using samples that are independently sampled from that distribution. And so, for example, you could have x1, x2, and so on and so forth, sampled from a common distribution P. These are real valued. And then the empirical mean would be estimating. So the question is, what is the common mean? And the empirical mean would be estimating this common mean. That's a good way of doing it. And by just using algebra, you can argue that this empirical mean can be calculated in a recursive fashion by taking the convex combination of the previous empirical mean with a new data, where you have this value of 1 over n, which plays the role of this alpha of n or something like that. So you could think about this as alpha n is equal to 1 over n. Then you could just write this that this is alpha n times, I guess you want to write alpha n minus 1, x bar of n minus 1 plus alpha n minus 1 xn. It's just the same, so that you see the parallel between the two. So new data arrives, that gives you the new target. The expected value of this target is what you're trying to estimate. So here you kind of have a noisy version of mu. You're blending that into the existing estimates. You're refining it, and as these coefficients are going to 0 at a particular rate, you're kind of rejecting the noise. You're filtering out the noise. In particular, you can easily calculate the variance of x bar n assuming that the variances of the variance of the distribution P exists, the variance of X bar N is the variance of X1 divided by N based on independence. So here we assume that the data is independent. And so that tells you that the distribution is concentrating, right? So the variance is going to 0 as N gets large. So that kind of suggests that, okay, so this X bar N is going to concentrate. The question is, where does it concentrate? Well, it's easy to calculate that the expected value of X bar N is just mu, right? Because the expected value is going to exist, like all of these expected values exist by assumption. And then the linearity of the expectation operator can be used. And you see that like you have N times mu divided by N. So that's just mu. So where does it concentrate? It concentrates around the true unknown mean. It gets better and better. And that's how this kind of learning of the unknown mean happens. It's kind of at the basis and the heart of all these learning algorithms that are dealing with rejecting noise. We can say here that the whole thing is just about rejecting noise. So X bar N can be seen as, or sorry, Xn can be seen as, oh, it's just mu plus some noise, right? When people talk about noise, they in particular mean that it's random and it's mini-zero. That's kind of when people talk about noise, that's what they mean. And so here, if I take the deviation of Xn from u, then that can be treated as noise. That is noise, in a way. That confirms this definition, right? It's mini-zero and it's random. Okay, so all that this tells us is that we should be evaluating the mean of this, but actually we should be, this is a complicated process, so we better evaluate the conditional expectation of this target, where we are conditioning on the state and all the previous data that happened before, but that's kind of summarized by this vector VT. And the last time we talked about this, I claimed that this is nothing but the Bamon evaluation operator applied to VT and this whole thing evaluated at ST. And that this follows just from the assumptions that we were following the policy pi. That's why the evaluation operator of pi comes into the picture, and the dynamics, the reward dynamics of the reward, and the state follows the dynamics of the Markov decision process. So this operator is defined in terms of this transition kernel and these rewards. So we learned that, okay, the purpose of this taking the convex combination is to gradually reject the noise so that this whole process is going to resemble of just using, like, getting closer and closer to these targets. But what's complicated here a little bit is that these targets do change. They depend on VT. It's not fixed. If we had, instead of VT here, if VT in this algorithm was replaced by V pi, then here we would have T pi, V pi, evaluated at ST. But we know from our previous studies that T pi, V pi is just V pi. So this is equal to V pi at ST. So that would be a good target. But VT is not V pi. So there is some error. And then the question is, whether these errors are going to throw off this whole process, and whether despite the errors, the whole process is still going to be convergent. So one way of studying this and maybe getting a gist of it is to just understand what happens if we replace and we get rid of the noise. So we can believe that somehow the noise is going to be rejected because these alpha t coefficients go to 0 at the right rate. So we just replace this target by its conditionally expected value. So if we do that, then we arrive at a new update equation that we would intend to study, which would be, and I just write the first arm of it. So, so for state st, we get this update that you get 1 minus alpha t times the previous guess at the state plus alpha t times, and now let me write this. So that's the target. Well, actually not this, but here we have Vt. So that's the key. We are still doing this, replacing the V pi with a Vt. So by the way, this was what we called bootstrapping, right? Okay. So now we arrive at this update process. And the question whether this is going to work or not. And here there is yet another something that's a little bit inconvenient. We're only updating one state at a time. And that state depends on where the trajectory goes. So earlier we had this discussion that if we expect convergence for all the states of Vt to V pi, we can only expect that if somehow this process, the states go everywhere, right? So the limiting distribution of where the states go when you're following policy has to cover all possible states. It's like a full coverage condition is going to be needed if we are expecting convergence. So here we see in this update that, yes, even if we didn't use these noisy estimates of that target, we would still need to argue that the states go everywhere, because if the states are, they are stuck in one corner of a grid web or whatnot, then only that information would be updated. And then there is no guarantee that the whole thing is going to converge. So I'm not going to deal with this part either. So I'm going to make another simplification. So this is simplification number 1, that I was just replacing this noisy target with the target that is estimating without noise. And the other simplification is going to be that I'm just going to recklessly assume that these updates do happen at every state. And then ask a question about, okay, is this going to work? Because if I do this, this still keeps one interesting aspect of the problem, and that is the bootstrapping aspect of the problem, right? Because I'm still using Vt in the target. What I was doing is that I was just simplifying by assuming that all states are updated in parallel, which if you only had a single trajectory, you can't do that. But you can imagine that in the long run, when these states go everywhere, then this update process is pretty close to this update process. And you can formally argue about the two. So I propose just to take a look at this. And let's argue about this process. And I'm going to take one more simplification. So since we're not dealing with noise anymore, it will be a little bit simpler for me if I just assume that these learning rate coefficients are constant. So I'm going to make the assumption that alpha t is alpha, and it's a number between 0 and 1. So then the only time-dependent quantity is Vt. Okay? And we can write this equation, because this applies at every state, in a much more compact form. We can just write that Vt plus 1 is equal to 1 minus alpha times Vt plus alpha times the Bellman evaluation operator applied to Vt. So we are effectively taking the convex combination of Vt and T pi Vt. And notice geometric picture might come back to you that I was trying to explain that you can have a vector Vt and another vector that's maybe T pi Vt. And so now these live in this S-dimensional Euclidean space, both of them. And the convex combination is just going to choose a value on the segment connecting these two dots. And for some fixed value of alpha, it's kind of like just, like wherever Vt is and wherever T pi Vt is, it's like with a fixed ratio chooses a point. So if alpha is small, then you can expect that this point chosen is going to be close to Vt. So this is where it's going to be for typical values for alpha, small values of alpha. If alpha would be 0.5, then we would be exactly in the middle of this segment. If alpha is smaller than 0.5, then you're closer to Vt than to T pi Vt. All right. And now we can still ask the question, does this work? What do we want from this? We want to show that Vt converges to V pi. So is it true that Vt converges to V pi for this new process, which was simplified tremendously compared to TD learning, but it still has the bootstrapping flavor of it? So what do you think? What can we do with this? Do you have any ideas about how to analyze this? Yes. Oh, that's alpha. This is alpha. Yeah. Yeah. Okay. So how shall we start? Like, if we are asking this question about, okay, we are updating these value functions, does it converge? Did we study anything similar to this? Have you seen anything similar to this? When we were updating and updating and updating, and we showed that these updates do converge. Yeah, fixed points do come to mind if we knew what the operator was. So fixed point means that you have an operator that takes elements of a space, maps it back to the space, and you try to find a point where things do not change. Then maybe we could apply theories of fixed point iteration, right? I think that's a very good idea. So the question then, what is the operator whose fixed point we are trying to find? What would be the convenient operator? That's true. T pi's fixed point is V pi. But maybe T pi is not too convenient to be used in this case. Maybe we can define some new operator which will be even more convenient, and we can just use our existing knowledge of how to analyze fixed point iterations. So the fixed point iteration, Banach's theorem, right, that we were talking about, the way it looks like is that you have this operator and you keep applying this operator. That's how you're getting new functions, new vectors. So if we want to apply this theorem, then we should take the leap and think that, well, okay, whatever we see on the right-hand side is maybe what the operator should be doing, right? So maybe define this operator, this new operator, T tilde, which will be similar to TP, but it's more convenient. It's tailored for our purposes. So it's just going to take some vector or function v, and it takes the convex combination of that function and t pi applied to that function. If I define this operator, then this update here becomes equivalent just writing that vt plus 1 is equal to t tilde pi, or p, applied to vt, because the way I defined the operator, and know it looks like as a fixed point iteration. The question is, whether this operator has the right fixed point. Should be v pi. We are hoping that its fixed point is v pi. That's one question. And the other question is, if we want to argue that this whole process is convergent, we needed some conditions to hold for this operator. Well, what is the condition that we wanted the operator to satisfy? Which is in Banach's contraction mapping theorem. Oops, that name. We want the operator to be what? Yeah, it should be contracting. It should be a contraction. Okay. So to argue that an operator is a contraction, we need to choose a norm or a distance. What norm or distance should we be choosing? What was the norm that we were using before? Not the Euclidean norm. Yeah. It was the max norm, right? So earlier we were arguing that t pi, t, all these operators are max norm contractions. So we like, okay, it's a natural thing to try first to see whether t tilde pi is still a max norm contraction. So let the norm of v be the max norm. And we knew that t pi is a gamma contraction with respect to the max norm. So now we need to check whether the same holds for t tilde. So for this, you take two functions or two vectors, v and u. You apply to each of them t tilde. And then you try to argue that the norm that you're getting for the difference between the two, the distance between the two, is strictly smaller by some contraction factor smaller than the distance was originally between u and v. Okay, so we plug this in. So plug in the definition. So this is the definition applied to just v. And then there is the definition that we need to apply for u. Okay. And then we can just, yeah. Evaluation operator. It is the same thing. So we introduced t pi, I don't know, like 5 lectures before. It's the same thing. it was coming from the data. So the distribution of the data follows the transition kernel. And that's kind of the magic of it. Like the data itself, its distribution, is bringing in the right information. The dynamics information is in the data, right? And so I skipped that part, but I was arguing that, so here the expectation of this target condition on, the state and the current value estimate brings in this operator, T pi. And maybe this will be an exercise. So it's a little calculation that one needs to do to show or argue for themselves that this is indeed the case. But you can feel that, oh, the data was actually generated by following the policy and then making a transition using the MDP transition. So that kernel should be showing up. That transition kernel should be showing up there. So it's a good question. It was a good question. All right, so going calculation. So it's just going to be a bunch of triangle inequalities. So arranging terms, I'm going to match this term, this 1 minus alpha v, with the 1 minus alpha u, and I'm matching the alpha times t pi v with alpha times t pi u, apply triangle inequality, pull out 1 minus alpha, pull out alpha. So instead of speaking, I should just write it. And so I get this. And this. So this is just because from a norm, you can pull out a constant. And by the triangle inequality, which every norm satisfies. And now we can use our knowledge that T pi is a gamma contraction to further upper bound this, because that will allow us to have v minus u showing up in this term as well. And once we do that, we have, so this is upper bounded by gamma times the distance between v and u. That's what we know about T pi. Gamma was the discount factor. And we have the distance between v minus u appearing here, appearing there. We put them together. And the constants that we are going to inherit is 1 minus alpha plus alpha. Wow. These markers are not the best today. Plus, there you go. All right. So just because T pi is a gamma contraction, you can get this. All right. So what do we see here? On the left-hand side, we have t to the pi v minus t to the pi v, the distance between the two. And we upper bounded it in terms of the distance between v and u. And there is a coefficient there. 1 minus alpha plus alpha times gamma. Can we conclude that this is a contraction? When would it be a contraction? When would t to the pi be a contraction? What do we need to check? That's right. So to declare victory and say that this was a contraction, it is sufficient if we can show that this is smaller than 1. So the question whether this holds. Okay. So one could try to do algebra or just remember this picture between convex combinations. So we have gamma. That's a number between 0 and 1. And we have alpha. sorry, so we have gamma. So this expression, 1 minus alpha plus alpha times gamma, I can look at this as this is taking a convex combination of 1 and gamma. So there is 1 and gamma, and I'm picking a point in this interval. I will get a contraction if I don't pick 1. So all the other values are going to work. When could I pick 1? I could only pick 1 if alpha is equal to 0. So alpha equals 0, that's not good. So we need to assume that alpha is going to be positive, and it's between 0 and 1. So here, get rid of this. Let's assume that it's strictly positive. And in that case, we get that t tilde pi is a contraction. What happens, by the way, if alpha is equal to 0? If we look at this process or look at this operator here, if alpha equals to 0, the data about the MDP would not be taken into account anyway, so that's kind of silly. Then the whole operator would be the identity operator. You take V, you return V. That's very silly. We don't want to do that. So alpha should better be positive. All right, so we can conclude we have shown that this Vt is going to converge to V pi as t goes to infinity. Just use Banach's contraction mapping theorem. Oh, not really. We only know that it converges to the fixed point of t tilde pi. Okay, so what's missing is whether V pi is a fixed point. That's enough to verify because Banach's theorem also tells us that for every contraction, you can only have one fixed point. It's just sufficient to verify whether V pi is a fixed point. For this, we can look at here. This is the definition. If I plug in V pi here, in place of V, do I get V pi? Well, there is 1 minus alpha times V pi plus alpha times T pi V pi. But we know that V pi is a fixed point of T pi. So this is also V pi. And so now we get 1 minus alpha times V pi plus alpha times V pi. That's happily V pi. So V pi is a fixed point, and we are really done. All right. So to summarize, teeter learning encompasses a number of ideas. There is noise rejection in it. So the alpha t coefficients are resembling this 1 over x coefficients. Then the noise is going to be reduced over time. And the other is bootstrapping. And the reason bootstrapping is not going to hurt us is because there is an underlying contraction that's happening. It's somewhat different than the contractions that we got used to before. And you might ask the question, what happens if, for example, I let alpha t go to 0 before ruling out 0? So 0 is not really our friend. If alpha t would go to 0 too fast, this is not going to work. So you better let alpha t not go too fast to 0. No, the question is, OK, how slowly do we need to make alpha t go to 0 for this process still to work? For that, you can do a little calculation, and you will get that as long as alpha t, the sum of alpha t is infinite, still converges. Alpha t is just a step size, yeah. That's right. And if you would let the step size converge to 0 too fast, then you would not be learning. That's what I'm saying, that there is some limit to how fast you can decay learning rates, because eventually if you do that too fast, then you stop learning, and that's detrimental. So the other option would be to keep alpha t a constant. If you keep alpha t a constant, you don't even decay, or you decay very, very slowly. Then the problem is that you're not really reducing noise. So if you keep alpha t a constant, then some residual noise always remains, and the process never converges. And well, that might be of a lesser problem if the noise level is well controlled. So you can go back to just averaging here and, for example, study this for a constant learning rate to see what happens if you have a constant learning rate, to get some insight into what happens. Like what can you expect? The same thing is going to happen with these more complicated processes. All right, so that's about for the convergence result, and I use almost all the time. Not much time remains to discuss the Monte Carlo versus TD issue. So let me do this. I will just summarize what I wanted to say, and I will put out the write-up, and you can read the write-up, and the write-up is going to have the details about what I wanted to say and explain. So the book is comparing TD and Monte Carlo, and there are some unique advantages to TD, and you should probably already know that very well because you went through a bunch of exercises. So what is the unique advantage of TD compared to Monte Carlo? That's right. Yeah. So because of the bootstrapping, you don't have to wait until the end of the trajectory. And as a result, if you have a continual, never-ending learning process, then like, how would you apply Monte Carlo? I mean, okay, hang on for a second. You can apply Monte Carlo by truncating the trajectories and then do other things. But okay, vanilla Monte Carlo cannot be easily applied, and it's going to be ugly if you do the truncation, and there's a bias that you incur. So TD seems to be kind of nice there. Although I have to say that TD is kind of doing, like, introducing some bias through this bootstrapping in the same way. So, but maybe it's, you know, a more elegant process. Okay, so that's one. And so if we want to study, for example, we want to compare Monte Carlo and TD, then maybe to create at least an example where Monte Carlo can take off without any biases, maybe you should be talking about an episodic problem. So let's take some episodic problems. So what's the next thing that you were taught about TD and Monte Carlo that in the comparison that you heard a lot? So is it advantages to use TD or not as opposed to Monte Carlo, and why? Let's say we are in an episodic problem, so we can run Monte Carlo. For neither of them, you need the model dynamics, so that's fine. They are on equal footage from that perspective. There is a statement, or like there is repeatedly stated that TD somehow is going to converge faster than Monte Carlo. And okay, so this is the myth that I want to bust. It's not true. So I can come up with examples where Monte Carlo is converging faster than TD. And that was my point, that like, okay, there is no clear winner here in terms of convergence speed. You have to manipulate the environment a little bit to make Monte Carlo converge faster, but I think that there are reasonable examples. So, and the reason the example that in particular comes to mind is very simple. If you have an episodic problem with a long chain, and there is a reward of 1, let's say, at the end, but you don't know it in advance, no rewards anywhere else. TD is learning. How does it learn? Well, it learns very quickly here, and then it needs to wait for this to converge, for this to converge, for this to converge, for this. And you are decaying the learning rate. As you are decaying the learning rate, there is less learning happening. So as the number of states here in this chain is increasing, TD can become very, very slow in learning the value of the very first state. Whereas if I take Monte Carlo, it just goes, sees 1, and it's like happily updates all the states, and it says, oh, for all the states, the value is 1. It's done. So, okay, the story is that It's not really black and white. It depends on the problem. People actually observe this, that sometimes Monte Carlo type of algorithms are working better. What's the good news? The good news is that you don't need to choose. You have families of algorithms that are very smoothly interpolate between the two, and then it just becomes a parameter, a question of choosing the parameters of those algorithms, so-called hyperparameter tuning. But if you know a little bit about the environment and you see that, okay, it has this chain line structure, for example, you have this chance of these errors, like the values propagating back slowly, then you already know how to tune this. Like then you want to do this delayed bootstrapping as much as you can. But in the other cases, when this is not the case, then maybe bootstrapping is going to be useful. All right. That was my bit busting about the unilateral advantages of TD, which do not exist. All right. Okay, everyone have a good weekend, and see you on Monday.